Sweet. I think we should probably like get started here. We got some people hanging out. Yeah, so I put like a poll on Mastodon and then later on Instagram about like what we should cover this time. And it was kind of all over the board. I put out options of talking a little bit about filters, talking a little bit about envelopes for like shaping sound with, or like also the idea of extending the oscillator that we built last time and making some more complex timbres with it, because like a pure straight sine tone is kind of boring. Everyone sort of voted for a different thing. So I think it's possible to talk about all of these things. Let's get started. I think with all of these, I want to try to build up everything from scratch in front of you. That way, if you weren't watching last time, there's not like, you don't feel like you were left behind. So we're just going to go to my little live stream folder. Let's make a new directory for stream 2. Okay. We're going to go in there. Start up our code editor. Sweet. So let's make a little C++ file. So really quickly, I'm just going to kind of recreate what we made last time. And, you know, like always, if you have questions about something, hit me up in the chat. Great. So last time we built a sine oscillator. Why don't I have syntax highlighting? Oh, because I'm not in main C++. Okay. There we go. That's so much better. Okay, so we made a little sine oscillator, and it was just, you know, a data structure that we attached a method to make it oscillate. And the data structure had a couple of things that it was keeping track of. It was keeping track of the phase, the current phase of the oscillator, so like where is it in time? And that's represented as a floating point number. And then we also had something that's the phase increment, which we shortened to phi for phase increment. And this is by how much does the phase increase with each sample, with each clock cycle. So, you know, digital audio, we are sampling it on right now on my computer at 48,000 times per second. So at each one of those times, by how much do we increase the phase? And this is what actually determines the pitch of the oscillator. If we increase the phase faster with each clock cycle, it's going to be a higher pitch. If we increase the phase slower, it's going to be a lower pitch. And so we gave this a method called next for next sample. And, you know, what we're doing when we're asking this to make sound is we're filling up a buffer of samples. Because remember last time we said that like digital signal processing is all about manipulating lists of numbers. And those lists of numbers represent the audio signal over time. So we're going to create a list of numbers one at a time by calling next over and over again to get the next sample in our list. And so each sample, we are going to figure out what the output of our oscillator should be. And this is a sine oscillator, so we're going to say sine of 2 pi times the phase of the oscillator. Okay, so that's going to give us a sinusoid. And we're going to want to return that output. But we've not done anything to actually affect the phase of the oscillator, and we want to increase it with each tick of the clock. So what we're going to do is we're going to say phase plus equals the phase increment. Okay, that's great. So now we're going to be increasing it at the right speed. And then we're going to say phase, if phase is greater than 1, because we want to constrain this between 0 and 1, so it just keeps repeating. If phase is greater than 1, then phase minus equals 1. So every time it sort of tips out of bounds, we're just going to subtract 1 from it and bring it back within bounds again. Okay, and this is just complaining because I need to import the CMath stuff so I can get my nice pi constant. All right, so now we have an oscillator that can make sound. The other thing that we did was we added a method to it to set the frequency. because thinking about like what the phase increment should be is not a very musical way to set the frequency. I guess suppose nor is what we're about to do. So we're gonna pass in the frequency in hertz, and we're also gonna pass in the sample rate. And the way that you compute the phase increment is it's just the frequency divided by the sample rate. Okay. The other little thing that we did was we made this little harness that we could use to listen to the output of our oscillator as we were going. So this is a command line program. We're just gonna sort of do the standard hello world program for C++. So that takes in an argument count, that takes in some arguments. All right, so we want to listen to our oscillator, so we're going to make one. Here's our oscillator. We're going to set its frequency is equal to, I don't know, let's do a nice low A. And then we're going to do const sample rate is 48,000 times per second. We're just going to let that get recast to a float from an int. We're going to make a buffer to store our samples in. So our samples are just floating point numbers that generally range between 0 and 1, or between -1 and 1. So here's our buffer. And we're going to do 4 seconds of audio, so 4 times the sample rate, because that's how many samples per second. So 4 times the sample rate is 4 seconds worth of audio. And then we're just going to fill this buffer up with a while loop. So let's have some counter. We'll call it processed. So this is going to be the number of samples that we processed, and we'll say while processed is less than we'll call this max samples. Let's pull this out. I feel like we should pull this out. This will be max samples. Okay, great. So while processed is less than that, we're going to increase processed by 1, and we're also going to fill up that spot in the buffer. So we're going to say buffer subprocessed is equal to osc.next. We're going to make that a little quieter because it's kind of loud. And then we're going to use this like kind of low-level C function to just write this to the standard out. What I said last time about this was like, if this part doesn't make sense, don't worry about it. This is sort of just a fun way to listen to some DSP algorithms without including any other external stuff. So like without adding the complexity of JUCE or pure data or some other environment where you could listen to sound. And I'm kind of excited about this. Like, I feel like this is a really interesting prototyping tool because you can spend like less than 10 minutes and start from a blank page and like already then be listening to your idea. Okay, so we give this some place to write to. We give this a buffer that we want to write data from. And then we have to tell it a little bit about the size of that data. So these are floating point numbers, and we have max samples of them. So we multiply those two together. Okay. We need to input or import standard out. We also need a header for this write function, and I can never remember where this thing is. So we're going to go look at what we did last time. Development. No. Fellhouse audio, live streams. Okay. What did we do last time? Here's stream 1. Here's our file as we left it. Okay, it was in, let me see if I can remember this. UNISTD. Sure. Sure. That means things. I know what that is. I have no idea what that is. Okay. Oops. Let's make it a little bigger again. So that's enough typing. Let's actually make this make sound. Oops. We'll use Clang++ as our compiler. We're going to give it, oops. Oh, this is the wrong terminal window. No wonder I was like, why is it small? Okay. Okay, we're going to say Clang++. We're going to give it main C++. We're going to tell it what we want the output to be. We'll call it sound. We'll call it sound. Okay, we compiled it. If we run it, it just prints a bunch of raw numbers to the command line, which looks like totally crazy. That's totally cool though, because we're going to run the sound program. We're going to pipe it to this utility called aplay, so that we can listen to it. We just needed to tell aplay a little bit about the nature of the data that we're sending it. So we're sending it one channel of audio, their floating point numbers, and the sample rate is 48,000 times per second. And we get 4 seconds of a sine tone that I hope was not egregiously loud. I might go turn that down a little bit for the stream, just because I have a feeling that was too loud. Please do complain in the chat if it is. So we got to the point where we sort of left off last time. We have our sine oscillator. So one thing that we might want to do is make the tone a little bit more interesting, because it's kind of boring to have just a straight sine tone. But we can do some frequency modulation, and it's pretty darn easy to do. So in order to do frequency modulation, there's sort of 2 ways to go about doing it. We could call this set frequency method every single frame, and make the frequency go up and down using another oscillator. There's a simpler way to do it. We can also send in a sample, the FM signal, whatever the modulator is. Maybe we'll call it modulator. So this is going to be what the modulating oscillator. We're going to set it to 0 by default because we might not want to do FM, in which case we'd call next without giving it any arguments. And in this case, we'll call next, giving it some kind of signal that's oscillating up and down. And every frame where we go to get our sine, we're going to be adding to the phase of the oscillator. So we have our phase of, normally that's controlling what the frequency of the oscillator is, and we're going to add this other signal to it. And this is actually equivalent to moving the frequency up and down and up and down. And if you're curious as to why, we can go into that. It's a little bit of algebra on the sort of sine function. Let's hear this make sound. We're going to make a second oscillator. We're going to call it modulator. And let's set its frequency to something different. Maybe let's set it to the A above. Let's set it to the A above the A of the other oscillator. And then we're going to pass in the next sample from the mod oscillator into the next function of our main oscillator. So this is how we do the modulation. Okay, I'm going to make it a little quieter because I feel like it was kind of screaming at us earlier. So let's compile it. Yeah. So we can hear that it's not just a pure tone, and that might even get more obvious if we pick a different ratio, like if we did kind of a strange one, like 1.5 0.33 times the sort of base pitch of our oscillator. We tune our modulator to that. We're going to get something that's got a little bit more fur on it. Okay, but yay, good for us. We made something that has a little bit of more of an interesting sound to it. Oh gosh, and there's just so much I want to say about FM synthesis. I might save some of that though, because we could, like, this is a rabbit hole that we could just disappear down for the rest of the stream. And if that sounds cool, like, let me know. We can do that. But I know there was interest in envelopes and filters, so I do wanna get to that a little bit as well. Ooh, okay. Right, didn't catch the whole thing, but interested in FM feedback. That is one of my favorite things. That was one of the things I really wanted to talk about. I'm so glad that you asked. So yeah, this signal right now, it's a separate oscillator, but we could use the output of this oscillator as the modulation input, and this is feedback, right? We can use feedback as the FM modulation source, and that's actually like really easy to do when you're working in something like C++, and like kind of hard to do in a lot of other audio environments. Like getting single sample feedback delay is sort of annoying in like Pure Data or Max or something, because like you kind of have to get under the block size. So we're just going to keep track of another piece of state as our loop is going. We'll call it last. And this is the previous sample. I mean, maybe it would be clear if we called it feedback. So here's our signal that represents the feedback. And so what we're going to do is we're actually going to write into that piece of memory feedback every time we increment the oscillator. And maybe instead of modulating it with the other oscillator, we'll just modulate it with the feedback. And right off the bat, we're going to notice something kind of interesting. It sounds kind of familiar, maybe. Oh yeah, I looked at single sample feedback and super collider a bit. Don't really like any of the methods. Yeah, you really have to jump through some hoops. And yeah, the point you get there, you're like, oh, gosh. So yeah, we just listened to the effect of just at unity gain passing in the prior sample into the next method of our oscillator. And I was curious if it maybe sounded familiar. The reason is if the pitch is the same, if we're just passing in feedback into a single oscillator like this, what actually happens to the shape is it starts to approximate a sawtooth wave. And so up until a certain gain, right? So at about unity gain, we get this sort of slightly dull sawtooth. And as we increase the gain, we start to get gnarlier and gnarlier sound. I'm going to make it even quieter because this is going to get kind of ugly. You can hear there's already this like high-pitched noise that's on top of the sound. And that noise sort of gradually takes over the signal as you increase the feedback. To the point where that's sounding like you can still hear the signal, but it's mostly sounding sort of like white noise. So that's the simplest feedback patch. But this gets, I don't know, we can play with this a little bit more, even just with what we've got right now. We could pass the feedback into a different oscillator. So we have the output, you know, the sort of final stage output, but we could pass that into the modulating oscillator, and we're going to get a different effect than if we passed it straight into the oscillator that produced the sound. Yeah, like I really wasn't sure what was about to happen, and kind of pleasantly surprised that we got this weird rhythmic thing out. Like, that's really interesting to me. And if we make it louder, what happens? Oh, gnarly. We still get the rhythmic thing, but we get like noise on top. That's fascinating. And I bet if we changed the modulator ratio, if it was 2.33 instead of 1.33, we'll get even weirder stuff. Actually, that's surprisingly similar. That is surprisingly similar. Okay, but to like make this musically interesting, I feel like we need to be changing the volume of this stuff over time. Like, not just the output of the main oscillator, because that would be amazing, but also like each of these stages where we have an output of an oscillator or the feedback is an opportunity to sort of shape the timbre over time. And in order to do that, it would be really cool if we had an envelope of some kind. And this is where I feel like we can build on the structure that we used for the oscillator, where we have a phase and we're incrementing it. But instead of creating this ramp shape, we're going to ramp up and then ramp down and then stop. But I wanted to draw some attention to this part of this structure here, where we have a phase, we have some sort of increment that we add to it every sample, because this ramp that we're making on the inside of this phase is making this sawtooth shape. It goes from 0 to 1. That's exactly what we want to do during the attack phase of an envelope. So let's make a simple attack release envelope. So we'll just spin up this structure here, and then we'll have a piece of state. It's a float. We'll call it level, and this will be the loudness of the amplitude at the current point in time. And then let's have an int that'll be like attack time in samples. So, you know, we could represent the attack time in seconds, but then we need to know the sample rate in order to sort of convert and make it useful for what we're about to do. So let's just go ahead and think about the attack time in samples. And let's actually make this a float as well, because it will make the math that we want to do on this easier if they're both floating point numbers, if they're both decimal numbers. So we'll also have a release time in samples. Okay. There's a little more that we need to do, but let's go ahead and start on the algorithm here. So we're going to have a next function just like we did with the oscillator. And just like the oscillator, we're going to be adding to the level over time. So the level is the thing that we're going to be returning, but we're also going to be modifying it a little bit. I'm actually going to make another piece of state here, call it out, because we want to manipulate level, but we want to do it after we have come up with the output to return, because we want the first thing that our envelope returns to be 0. That way there's not like an unpleasant popping sound at the beginning. So if I just think about what this does right now, it returns 0. So we want to make the level different over time. So we are going to add 1 over the attack time in samples, each frame. So every sample, we add 1 over the attack time in samples. And this is going to make a ramp that goes from 0 to 1, and it takes the amount of time that we want, the attack time, in order to go from 0 to 1. Does that make sense why that would be? Because every frame we're adding 1 over that. So if we just think about this fraction increasing, what the level is going to look like over time, frame 1, it's going to look like this. And then the second time we call it, the level is going to be this, and then, oops, my mouse is over it, and this, and then this, and this, and then this, etc. Until we get to a point where we've got the attack time over the attack time, and we've reached 1. But without doing anything else, it's going to keep going. And we don't want it to keep going. We want it to stop when it gets to 1 and start ramping down. And this is where we need some sort of conditional logic. And the way that I like to do this is I like to use an enum, which, if you've not seen it before, is just a number. An enum is just an integer, but we give the integers names to represent certain states. So we're going to make an enum, and we're going to call it stage, because this is which stage of our envelope cycle that we're in. Are we in the attack stage, or are we in the release stage, or maybe are we off? Is it not actually running right now? And we'll call this stage, and we'll hold on to it, and it equals off by default. Okay. And then what we can do in here is we can use a switch statement. And a switch statement is just, it's like an if statement, except it's a little bit easier to deal with multiple conditions. So we're going to switch on the stage, and this is an enumerated type, and the compiler knows it's one of these 3 things. The stage can only be one of these 3 numbers. And then it's smart enough to actually fill in what those are. So then we have cases for attack, release, and off. And each one of these cases, we want to do something slightly different. So in each one, we want the output to be the level. And at the end of each one, we want to return the output. But if we're in the attack phase, then we want to do what we were just doing here, where we increase the level. If we're in the release phase, then we actually want to decrease the level by 1 over the release time in samples. And then if we're in the off stage, the level equals 0. If the envelope's off, then it should be silent. Okay, so now we have the difference in the algorithm for each one of these stages. We're either ramping up, or ramping down, or we're off. Now we just need to make it go from one stage to the other. So if the level is greater than or equal to 1, then stage is equal to release. And then in release, we can do something similar. If the level is less than or equal to 0, then the stage is off. Okay, there's a few other things that we could do to this. Like right now, it's sort of theoretically possible if we were modulating the attack time, that we would end up overshooting 1 or going under 0 and producing a negative number. And we could write a little bit of code to sort of defend against those cases. But right now, this is enough for us to actually make some sound with. so let's make an envelope. Here's our AR envelope. I'll do it down here. Oops. And we'll say that the attack time in samples is equal to, I don't know, half a second. And to convert from seconds to sample rate, we just multiply by the sample rate. Okay, so we have our attack time in samples, and then we'll have our release time in samples, and maybe we'll have this be a second, a full second. Okay, and let's actually call our envelope ENV. I think that might be a little bit easier to keep track of than calling it AR. Okay, so it's called ENV. All right, so to then modulate just the loudness of the sound over time, we can say env.next here. One thing that we forgot, we also want to turn our envelope on. So we'll say env.stage equals attack. So this will just initialize it in the attack phase. Oh, it doesn't know what attack means. That's because we have to say AR envelope : attack. Okay, so this just sets that stage so that we start here and we ramp up. We immediately ramp up. And so if we did everything right, we should hear a sound that starts from silence, gets louder, and then gets softer. Nice. That's cool. I'm gonna make it a little bit louder now. I feel a little bit less scared of it now that we've got an envelope on it. Yeah. It's sort of similar to the way that the oscillator works, right? So what would happen if we started putting some envelopes on these other things? So maybe we have envelope sub M, and that represents the modulator signal, and we have envelope feedback for the feedback path. And then we could sort of set all of these to different times where we're setting the modulation envelope. Maybe it has a slightly slower attack and a slightly faster release than our main envelope. And you know, for our feedback envelope, you know, maybe we want like actually a really, you know, fast attack and a kind of short release. Oh, whoops, we forgot to actually use any of the we forgot to use any of the values. So env sub m dot next. Okay, so now we're actually using all the parts of the signal. And now we're getting something that's a little bit more timbrally interesting. You know, one thing we could do that I love to do with FM signals is make them percussive. So we could set this initial attack time to be something really, really short. And then we could also take this feedback signal. I want to put it in the main oscillator so that it's not being cut off by this modulator envelope. And we're going to make the feedback oscillator also really short. And we're also going to make it kind of loud. Because remember what this is, you know, when we were playing with the feedback earlier, it was adding noise to our signal basically, and so we can create this little puff of white noise at the beginning of the sound, and that helps make it sound percussive. It's almost like the pick scrape that you get when you're playing guitar, or the sort of noisy impulse you get when you strike something. Yeah, that was kind of cool. I want maybe a little bit tighter of a release time on that. That's kind of cool. Maybe even a little bit tighter. That's maybe too tight. All right, that's pretty cool. But what's kind of nice about this now is we have a sound that has some animation to it. It's got like a really bright, sharp attack, and then it has some evolution to it after that. It gets warm and then cold again. Cool beans. We have an envelope that we can use. I feel like we could make it a little bit just nicer to use by making some little helper functions, some methods on here to help us set these pieces of state. So just like we had set frequency on the other oscillator, we could have set attack and release. Maybe like set envelope. Yeah, set envelope. That sounds cool. And this will be attack times seconds, release time seconds, and the sample rate. And we can just say attack time samples is equal to attack time seconds times sample rate. Then we can do the same thing with release. Is that working? Oh, did I forget to? Oh, I forgot to do S. Yeah, there we go. Okay. So we've actually set our envelope. And then maybe we also want a little function that's like just to trigger it again. So we can say trigger, and we'll say stage is equal to attack. And we can say level is equal to 0. Okay, so this will reset our envelope and get it going again. All right, and then I'll just replace this stuff. We can come up with some different envelopes. I think that would be fun. So we can say set envelope. 0.01. Maybe this will be 2 seconds. This is the sample rate. Here's one for the modulator. Here's one for the feedback. And then we'll just say, we'll trigger each one of these. So I don't know. I think that helps make it just a little bit more clear what it is we're doing. So now they'll all have the exact same envelope. Actually, I don't think I want that. I think I want the feedback to definitely be a bit shorter. Sweet. Okay. So this is pretty great. I mean, we could make a whole plugin just off of like really simple FM stuff. One thing I'm kind of craving though is an envelope that's a little bit more percussive. Like we've got our sharp little burst of noise at the beginning, and it's nice and tight, but I would like to have a shape that we don't have access to right now. We've got a shape that's basically just a line, a ramp, and it's a very steep ramp. But I would like I would like sort of something that looks a little bit more like exponential decay. Because I think that sounds just a little bit more realistic and physical. It's really good for making percussive sounds when you have an envelope that like starts off really loud and then gets softer quite quickly. And exponential decay does that. And I wanted to show you a way to build an exponentially decaying envelope in sort of a way that, if I tip my hand a little bit, in a way that actually has us build our first filter. Okay, I'm just gonna call this perk envelope. I'm not gonna reveal what this thing is. So I think this is the way I'd like to do this. I'm gonna build this up. We're gonna listen to it. We're gonna sort of verify that we get the sound that we were interested in, and then we can sort of explore why it is that that worked, if that's interesting. So, you know, maybe a little bit similar to how we're doing with the feedback down here, where we're just keeping track of this extra piece of state, and it's a single sample delay. We're going to keep track of the prior output of our envelope. And for reasons that might become clear later, we're going to call this yn1. Okay, so this is the previous output that our envelope produced. Let's initialize that to 0. And then we'll also keep track of a piece of state that we're going to call A1. And this will initialize to something very close to, but less than, crucially, but less than 1. And the thing that we're going to do, we're going to make a next function that actually takes in an input. We'll call that input x. Every frame we're going to produce an output. And that output is going to be equal to the input plus the prior output, but reduced by this coefficient, this A coefficient. Okay. We're going to return that every frame, and then we're going to make sure that we set the previous sample here, so that the next time it gets called, we have access to whatever we came up with here. All right, so now we have this thing, and I'm claiming that this is an envelope. So let me try to prove that to you. Let's have the sort of main envelope here be this perk envelope thing. And then we're going to say envelope y1. We're just going to go ahead and reach into that structure and set it equal to 1 in order to trigger it. And then what it's going to do, well, we'll see. We'll see what it does. And I'm just going to feed it 0 every other frame. So every input is going to be 0, except for this one that we sort of seeded as 1. Okay, so let's see what this did. Ooh, it's very percussive. That's interesting. Okay, let's make our feedback envelope one of these percussive envelopes as well. Okay, just gonna comment out this stuff from when it was a different kind of thing. Alrighty. So our feedback is now also one of these percussive things. Oops. Oh, right. Okay, cool. It's actually a little bit longer than I wanted it. I was hoping that the feedback would have gotten shorter and more percussive. So how do we actually change the release time of this? And why is it that this thing is actually producing this sort of exponential decay that we were looking for? So let's maybe take a look at how this thing is working, and we can maybe take a guess for how we do what we want here. So let's think through what happens when we feed this envelope the following signal. So these are the values of x over time. So we have some signal x, and it's 1 for the first frame, and then it's 0 for all of the other frames. Okay. What happens when we feed it that signal? Here's our basic sort of relationship for our recurrence relation for the filter. Each sample is equal to the current sample of x plus a1 times the prior sample of y. But the prior sample of y is something that we can sort of expand, and that's equal to the previous x plus the previous y times a1. And then that's something that we can expand. That's equal to the previous x plus the previous y times a1. Oops. Okay, and if we can sort of notice a little pattern developing here, right? If we do a little bit of algebra, we can see that we get the following sort of series forming. How do I want to represent squared? Let's do this. Does that make sense? Why we would end up getting this sort of series? And so on, forever and ever. And when we feed it this signal, we're starting with 1, and then we're getting 1 with this number times this number that's slightly less than 1, and then we're getting 1 with this number squared and cubed, and so on and so on. The power just keeps increasing. Every time we multiply a number less than 1 by itself, we get an even smaller number. So every frame, we've got this thing that started as 1 and is just decaying by something that's in the exponent. And that's why we're getting exponential decay. So this is a sampled exponential decay. And this thing that we just did here is called an impulse response, because this isn't actually a percussive envelope. This is something called a one-pole filter. So I'm just going to rename that one pole. And the reason that it's called one pole is because it makes use of one of the prior outputs. And we can talk about like why that is later, where that name comes from, and the different like ways of characterizing filters. But right now, I think it's good to just say that it uses a prior output, and that's why there's one. It uses a single prior output. And if it were using prior inputs instead, we'd call it 1, 0. But it's using a prior output, so we call it one pole. Okay, and the impulse response of a one-pole filter is an exponential decay, provided that this number is less than 1, right? Because what would happen if this number were 1 or greater? We would end up with a series that actually isn't bounded. It would just grow and grow and grow and grow and explode. But provided that this is less than 1, we get an exponential decay, and it shrinks. The speed at which it's shrinking is controlled by this coefficient, by this a. So in order to make our other feedback envelope, shrink at a faster rate, right? Because we wanted this to be this little puff of noise at the beginning. We just set it to a smaller number. So let's set it to 0.9 instead of 0.999 and see what that does. It's like quite a big difference, right? All of a sudden, it's just this tiny, tiny little puff. Oh, now we get a real click. That's kind of cool. And if we do 0.999, oh, I think I forgot to compile it. That sounded exactly the same to me. Yeah, there we go. Now we get a little bit more of a burst. But this is not a very intuitive way to control this time, right? Like, what does this number mean? It's not in seconds. So how might we actually make this one-pole filter into a more effective envelope that we can control the same way here, where we're using an attack or a decay? This doesn't have any attack. It just starts straight off. And in order to learn how to do that, we're going to turn to our friend Julius Smith. So if you don't already know about this website, this is an amazing website. This guy, Julius Smith, he's a professor out at Stanford, at a part of Stanford called CCRMA, CCRMA, the Center for Computer Research in Music and Acoustics. And he wrote the book about filters. This is a free textbook on digital filters with audio applications. So this is Introduction to Digital Filters with Audio Applications. It's a great book. If you want to learn more about the math behind filters, you can read this for free. There's problems at the end of each chapter. You can just kind of take a free course in audio filters on the internet. But part of this, in the discussion of one-pole filters, is this approximation for the decay time constant. This is how long a way of expressing how long it takes for an exponential to decay by a certain amount. Because something that's kind of funny about this filter, this one-pole filter, is that it's said to have an infinite impulse response, right? This sequence gets closer and closer and closer to 0, but it never quite makes it all the way to 0. So it has an infinite response, but we can say some things about the amount of time it takes to get to a certain percentage of its original level. So this time that is on this Julius Smith page, tau, decay time constant, is the amount that it takes for the filter to decay by 1 over e, the number e. And that's pretty handy, but 1 over e is still going to be fairly audible. So there's actually another way of expressing this time constant that gets called T60. So here's what tau does, right? This is a really good picture for this. So tau is the amount of time that it takes to get here. We're 1 over e from the original value. T60 is the amount of time that it takes to get here. And this is going to be perceptually silent, guaranteed. So if we want to characterize the release time, T60 is a pretty good way to do it, right? This is going to be the amount of time that it takes for our envelope to go from fully loud to fully silent. And like probably perceptually, it's pretty silent around here instead of here. But let's start with T60. And these things are actually related to one another. So T60 is equal to the natural log of 1,000 times tau, or approximately 6.91 tau. And we can get this is an estimation of tau. We can get an exact approximation of tau. This R right here, this R is the same thing as our coefficient AN1 or A1 that we had in our filter, right? R is the same thing as AN1. When we say the radius of this pole. And that's equal to E to the negative of the sample rate over tau. So T, uppercase T represents the sample rate, and tau represents the tau time. So let's see if we can write a little function for set decay. So this is going to take a decay time in seconds, and this is going to take a sample rate. Okay. And the goal of this function is to set A1. And A1 is going to be equal to E E to the something, and we have to find out what that is, right? We have the sample rate. That's good. We don't have tau. So let's find tau. Oh, I told a little lie earlier. I said T is equal to the sample rate. That's not quite true. T is the sampling period. So T is equal to 1 over the sample rate. So the sample rate's in hertz, and we want 1 over that. We want the amount of time in seconds. And tau, we said, is related to this thing T60. So this is our T60. This decay time in seconds is our T60. And we know that these are related by this. So we do a little bit of algebra. We can take our T60 and divide it by 6.91 and have a reasonable approximation of what tau is. So we can say T60 divided by 6.91. All right, great. We have tau. So this is equal to negative T over tau. And now we should have a function that lets us set our decay in a more legible way than this. So we can replace this line. Okay, so now we can call this set decay thing. Oh, and something I just want to mention, like, maybe you're not interested in the math part of this. That's totally fine. Like, I think if you're an artistic person and you're just trying to use this stuff to make sound, like you want to make synthesizers, the math part of it is not as interesting. I think it's totally valid to approach this as like a recipe book. You know, and just because there's tons of algorithms already out there. I think it's really fun to just like go ahead and build some of these as recipes. So I hope that like if the math part of this is like not so fun, that the you don't need it so much, right? If you're not interested in the why, you can still make a lot of really cool sounds. And that's really what we're after here. That's like the point. Okay, so we're going to set these decays to different things. Okay, so all right, let's have this take a second to fully decay, and this will take 1/10 of a second to fully decay, and see if we've done anything here. Yeah, that's sounding more right. Is it really a second though? Yeah. Yeah, it's about a second. I think that's nice. Cool. So we now have two different kinds of envelopes that we can use. One of them is our first filter, this onepole, and the other one is this attack release envelope. We've done some FM. We've like made a sound that is timbrally a little bit more interesting. We're using feedback to get this nice puff of noise at the beginning of the sound, which is like one of my favorite things to do with it. This is feeling pretty cool. Let's put this in a plugin. So the way we did that last time is I'm gonna open up another terminal. We had downloaded the JUCE source code. And the JUCE source code ships with this program called the Pro Juicer. I think it's in extras. Yeah. I think it's in here. Okay. Pro Juicer. Bink. Okay. So we're going to make a new plugin. Call it FM Percussion. Will be the name of our plugin. We'll leave this at defaults. We're not actually going to use any of this stuff. We're not going to give our plugin a UI. We can check the different platforms we want to support. So let's say Mac and Linux for now. We could support Windows as well. I'll check all of them. We're only going to use the Linux one though today. We're going to create it in our little livestream 2 folder. Okay, good deal. Yay. Good for us. We're gonna say that this is a synth. So we're gonna need MIDI input. So this automatically sets the type to the type that we want. That's all very good. We save it. Okay, and now if I look over here, I have this new folder for the source code for our plugin. Very cool. Let's just make a little header that we can put all of our good synthy goodness in. So we're gonna add, we'll call it synth.h. Okay. Pragma once. We only want to include it the one time. And let's just take all of this good stuff. And we can put this in our little header. And then let's actually like let's use the stuff that we were doing in our main function, and we'll make a little struct out of that. That way we don't have to like rewrite it. It'll make the code that happens in the processor a little bit easier to understand. So let's make this struct, we'll call it synth. And synth will sort of be the composition of these other things. So we're gonna say, let's make a little set frequency function that takes in a frequency, it takes in a sample rate. Huh. Okay, we also have this stuff in our structure. Being a little messy here, but I hope that's okay. And we'll have some function trigger that we use to turn on the envelopes. Just gonna get rid of the little comment bits. Oh, I guess trigger must take in the sample rate as well. Okay. oh yeah, this was part of it as well. Oops, my bad. This isn't this isn't trigger. This is actually set. I don't know, set decay or something. I don't know. We're sort of like eventually this will be set decay, but we're hard coding all of this stuff. So I don't know, let's just call it init. This is just going to initialize all of the values to something that we want. And we can talk about how to hook up knobs and buttons and like make a little simple UI that we can control our plugin with another time. But right now it's just going to be one hard-coded synth patch. Okay, and the thing we're missing is this next function. So we'll make a next function that lets us do all of this stuff. So we've got our envelope for the amplitude. That's equal to envelope.next. We've got our envelope for the modulator. That's equal to the modulator envelope.next. Wait, was that mad? Oh, right. It doesn't take anything. Right. That one's an attack release envelope. The other ones are percussive envelopes. And we have our one for feedback. That's the feedback.next. Feed that as 0 because it's actually a filter. Okay. So that's going to be our main oscillator. Oh, right. Ha ha ha. So our output is going to be equal to the main oscillator, and we're going to modulate that with the feedback times this feedback envelope, and then we're going to modulate this with the mod oscillator.next times this modulation envelope. Good deal. We're going to set the feedback equal to the output. We're going to return the output. Oh, whoops. There we go. Oh, yeah, and then we want to set. Yeah, okay. So this will actually apply the envelope to the whole sound. Great. I think this is basically the same synth patch that we had before. It's maybe a little bit neater, a little bit easier to see. All right, so we have this structure. We want our processor to have one of these. So we're just going to make a little private piece of state in our processor. We're going to just kind of ignore all the boilerplate that JUCE made for us. We'll call it synth. Okay, amazing. And then in the processor, there's sort of two methods that we care about today. One of them is prepare to play, and the other one is write, what is it called? Process block. Process block is the other one. So prepare to play, that's the first one where we get access to the sample rate. So this is a good time for us to initialize our synth, because now we finally know what the sample rate is. And we can set the decay times of our envelopes and all that good stuff. Okay, the other one is process block. In this one, this is where we got confused last week. Okay, this week I hope that we can get unconfused. So we're gonna have some piece of state, which is the number of samples that we have processed, and we are going to iterate through our MIDI messages. So each MIDI message, we're going to say message equal to .get message. I think that's how this works. It would be it would be nice if it if the syntax highlighting weren't screaming at me and I could get some autocomplete going. So let's fix that real quick. Let's CD into what's going on? CD into FM percussion builds Linux makefile, and we're going to do bear. This is going to give us compile commands so that my editor actually knows what's going on. This will take a minute, but we'll let that cook in the background while we're messing around in here. So we're going to iterate through all of our MIDI messages. And then we'll say while processed is less than okay, I'm going to cheat a little bit. Look at last week's code. So here's last week's code. We iterate through our MIDI message. We say get message. All right. Sample position. Okay. So yeah, let's take this. So we're iterating through. We get our message. Then we get when the message is in samples. So the first thing that we need to do is actually process up until that point, up until the point we want to apply our node on message. This is probably a node on or a node off. So while processed is less than that, we increment processed, and we go ahead and process our buffer. So we can say float out is equal to synth.next. All right. We've actually processed our signal, but we need to actually write it out. So we're going to, and we have 2 channels to write it out to. So we're going to take this bit of code here. That didn't do what I wanted. There we go. We get a right pointer to each channel. So that position in the left channel and then in the right channel is equal to our output. Okay, good deal. So where's the bottom of this for loop? I feel like something bad happened. Okay, there's the bottom of that for loop. Great. So we've processed up until the point of time where the MIDI message comes in. And then we want to say, then we actually want to figure out what this thing is and do the right thing according to that. So I think there's a method. It doesn't like synth init. Why not? Oh, right, because we didn't import anything. So we can say we can include the synth header. And we can copy these compile commands that got created, up 1, up 2, up 3 directories. 1, 2, 3, 4 directories. Let me start there and see if that's right. Yeah, that sounds good. I'm gonna quit my editor and open it again. Okay. Now this should look a little nicer. Oh my God, that's so much better. It's not screaming at me. Okay, where do we leave off? What were we doing? So we've actually worked our way up until that point in time where the message happens, and then we want to actually apply the message. I'm just going to cheat from last week. I don't think there's any shame in that. So now that we know we're up at the right point in time, we can figure out if the message is a node on, and then do the right stuff essentially, right? So if message.is node on, then we can say synth.trigger. Oh, it takes the sample rate. That's silly. It doesn't actually need to take the sample rate. We'll fix that. Synth.trigger. Oops. Okay. And we'll also want to set the frequency. So we can say synth.setFrequency is equal to message dot. How do you get data out of this? Like get MIDI note in hertz. There we go. Oh, of message. I think that's how you do that. Okay, so that'll give us the frequency in hertz associated with that MIDI note. And then we have the sample rate, right? No? Okay, I feel like that's kind of silly. We should have the sample rate. We should know what it is. Okay, let's put a little piece of state in. I don't know, why not? We'll put it in the synth. Yeah, we gave it the sample rate here. We might as well remember it. And then this doesn't need to take in the sample rate anymore because we know what it is. Okay, great. So we're in our processor. Oh yeah, we just don't need the second argument. Okay, good deal. So if it's a node on, we set the frequency, we trigger the synth. That's great. We don't actually need to worry about node offs because we have this percussive envelope and it'll just like pew. All right, so this will process all of the MIDI messages. The only thing that we need to do after this is process any audio for the amount of time where we didn't have any messages. So we might get through all of this loop, and processed will still be less than the total number of samples in the block that JUCE wants from us. So we're just going to put a little while loop at the bottom to catch that case. So while processed is less than buffer.get number of samples. So while it's less than that, we're going to go ahead and do this again. Boop. And this is where we got confused last time. This defaults to the total number of input channels. We actually want the total number of output channels. That's why like last time, our plugin was silent and we couldn't figure out why, and it was really frustrating. Okay, there we go. And then we don't need any of this boilerplate crap anymore. That goes away. All right. So here's our loop. And what's kind of nice now is we don't actually have to touch the JUCE stuff anymore in order to get sound out. Like we could change the implementation of synthesizer.next in order to change our sound, and this just stays put, which is cool. Okay, so let's actually compile this thing. Make. I feel like we're not actually getting our note messages. Like something is screwed up with the project setup. So let's go back, open up the producer again. Okay, we have our FM percussion synth. Oh, plug in MIDI input. Do I have to check that? I probably have to check that. That's silly. What kind of synth doesn't have a MIDI input? I think that was it. I think we're just compiling without MIDI input. Okay, Reaper. Making a thing. We're making a thing. It's not screaming. That's expected. That's good. New MIDI item. Yes! Amazing. Okay. So, yeah, apparently okay. Every time we do this, we learn a little bit more. You have to check both of these if you want it to actually work. It takes MIDI input, and it is a synth. I don't know how you were planning on triggering your VST if it didn't take MIDI input, but okay, cool, fine. Whatever, Juice. That's weird, but that's your business. Okay, great. Now we have a synth. It sounds good. Like I would use this sound. This is a cool bass line. Oh, Reaper. Oh, MIDI editing in Reaper. It's just not very fun to edit MIDI in Reaper. We've been on for a long time now. We should probably stop, but I kind of want to celebrate. I want to celebrate our victory. I want to make an envelope that's for the pitch. Okay. We're going to make an envelope for the pitch. And then down in our next loop, we're actually going to set the frequency. We're going to make a piece of state to store the frequency. We'll replace this. Okay, that's cool. So then we can say here, we can say frequency. We can say frequency times ratio. We're going to save this out as ratio. We'll make a piece of state for that. Oh no, I wasn't actually typing. Sad. Okay, we have a ratio, we have our frequency. We're setting it every frame. The reason that we're doing that is because now we're going to add an envelope for the pitch. Because I want this thing to be a little bit more drum-like. So this is going to be times 1 plus E sub P. Yeah. Now we're going to have something that goes like pew. And I think that'll be cool. Yeah, anything else that I want to do this? I feel like the feedback. Oh, yeah, let's add in all the rest of our like envelopes here. We have our E feedback, we have our modulation envelope, E sub M. That was just E sub F. Okay. Whatever. Cool. Cool. Okay, yay. Reaper. Yeah, just opens up our last project. That's nice. I should have saved it like a long time ago. Yeah. That's a fun bass line. There's a little bit more that I want to do to this because I want it to be way more drum-like. And right now, the transient that I'm hearing is slightly different every time. And maybe you want that. Maybe you want that, but I don't want that. I want the transient to be exactly the same every single time that it triggers. So what we're going to do is we're going to reset the phase every single time that we trigger the oscillator. We're just going to set the phase to 0. And let's do it on just the main oscillator and not the modulator. I think that will sound, that'll be kind of like the best of both worlds, right? Because if we reset the phase on all of the oscillators, we're going to get exactly the same sound every time we trigger the synthesizer. And I feel like that's losing out on some of like what's cool about synthesis. I think it's cool that the sound's a little different every time. Yeah. That's nice. It's not too clicky. I can hear that little pitch envelope though. It's giving us a nice little transient.